Good morning, everyone. I'm going to present Insight. This is a joint work with our colleague, Nguyen, Kamal, and my advisor from NC State University. So before I talk about Insight, I would like to talk about what kind of service we target. Here we focus on online services. What I'm showing here is one example of online services. Which is a virtual computing lab we use at NC State University. It is used daily by more than 8,000 users, students and faculties. We are all using it. So you can see that's it, distributed and complicated system. So it allows user, it's very similar to Amazon In-situ. Basically, it allows user to submit a request through a web server, push to the database server, and we have the reservation server to process the request, make a new VM, and net the user to use the VM. So here, because the reservation server is the most important component, so we focus our diagnosis efforts on this component because it accounts for most of the failures in the system. Other online services we can consider could be a normal web server or database server. So as we all know, the online services are expected to work 24/7. However, the online services are very prone to failure, especially the long-crossing failure. This is some statistics from the research I have. So you can see in 1 month it has 154 failures, and last year we have more than 1,800 failures. So non-crossing failure usually go unnoticed because it doesn't cross the system. Also, even though sometimes it generates some console log messages, however, the console log message doesn't explain why the failure happened. I'm showing here 2 examples. The first one is from the light TBD failure, in which there are low proxy. It said no proxy config with the system. However, the true reason is because of a bug in the code. The second one is from authentication failure in VCL because of some missing private key. But it said it's normally just said request fail without explaining anything. So existing approach proposed a couple of solutions. The first one is offline failure reproduction, in which the failure report is sent back to the user, sent back to the developer, so they can reproduce the failure offline and try to understand what went wrong during the production run. However, this is really very hard because sometimes we don't have enough information. We don't have the other components that interact with the faulty component, or sometimes it's just because we don't have the third-party software to install at the developer side. Second approach is the record and replay, in which basically it's a variation of the first approach, in which the software developer are provided with actual information. This is recorded log the execution run of the failure. So it's easier for them to reproduce the problem. However, this requires intrusive system recording, which might incur some overhead, privacy concern, or sometimes it's kind of hard to deploy in the production environment. So the third approach is the on-site failure diagnosis. Charles is the first is the one who proposed diagnosis failure run at the end user side. So it relies on repeated replay to compare the good runs and bad run, and from that it figure out what went wrong with the bad run. So it requires trick pointing to perform repeated replay, and also it performs diagnosis directly on the production component, which might incur long service downtime. And we also observe that even though it performs at the end user side, but it not fully leverage on the environment information. So here come our key observations. So we observe that production environment provide a lot of important clues, such as inputs, configuration file, interacting components, console log messages, or system call chases. So if we could leverage this kind of information, we could perform much better, much efficient failure path search. The reason is because we're going to have a much more smaller search scope. One example is if we know the NITBD system, the failure I said before, it can fit with the round robin policy. We don't have to explore other policies. Also, the last one is if we could decouple analysis from the production run, we can minimize service downtime. So we do this by using the dynamic virtual cloning to capture the failure moment state. So I'm showing here our approach. So same system, the VCL system I showed you before. If we detect the failure happen at the reservation server, we're gonna clone this faulty component to create a shadow server, and instead of perform directly on the production component, we perform our analysis on the central server. So because, as I mentioned before, we want to leverage the environment information, so we still allow this component to interact with other components in the system. Of course, we have to perform, to prevent some side effect that the shadow component might cause on the production system. I'm going to talk about in the coming slide. And on this server, we perform binary execution operation. Basically, we leverage the environment information to perform search on the binary directory. And the output is the match failure paths that produce the same runtime output as the failure run. So there are a couple of challenges we have to deal with in order to build In-situ. The first one is that usually we don't have the source code access, so we use a binary-based approach. We also want to achieve fast failure path inference, so we do this by leveraging the fresh environment data at the failure moment. We also want to achieve the low runtime overhead because we don't want to. We want to people use our tool, so we don't use the intrusive recording in our system. We also want to support different systems that's written in different languages. The compiled programs like C, C++, or the integrated program like Perl or Java. So we build In-situ based on two basic building blocks. The first one is a dynamic central server creation, in which we use the 9VM cloning to decouple analysis from the production run. The second one is a guided binary execution operation, in which we leverage environment information to search for, as a guidance to search for the failure path. So because of binary based, so we don't require the source code. So here is a detail about dynamic shadow server creation. Basically, the first step when we clone the faulty component, this component gonna inherit all the state from the production server. So the first step we have to perform is we perform automatic reconfiguration, in which we have to reset the IP addresses if needed. We reset the firewall to allow this component to interact with other components in the system. And as I mentioned before, we want to protect our system from the side effect of the central server. So we use a policy-driven output filtering proxy. Basically, the idea is we want to drop unwanted communication between the central server with other components, such as we only want to allow the read access to the database server, but we want to block the write access to the database server. So it won't change our database server. Here is a guided binary execution operation. So I will walk through this example. On the left-hand side, I'm showing here is a console log message from one VSL failure. It's only two console log messages from a subset of console log messages. And on the right-hand side is a code, a piece of code from VCL. So inside first execute the code. You can see that's the first one. It generates first console log message. Go to the first branch. It could be a truth value, so it may generate different console log messages compared to the second one. Inside monitor this and detect it. It roll back to the previous branch. Try with different value for this branch. Try with false value and come to the second branches. Again, it's try with false and true condition here. For the true, it's generated different console log messages, and for the false value is then a match console log message, and this is the execution for this code that inside I want to find out. So the idea here I want to tell you is that we just want to use the environment information as a guidance to prune out the unwanted, the wrong path. So this is only a basic scheme. We have a more complete scheme in our paper. Please check it out if you're interested. So here we also intentionally checking, skip checking the constraint because we want to achieve fast inference path. So because we can leverage the environment information, we found that the infeasible path might be a very rare situation. Also, inside able to find out multiple match paths, so we can perform checking the constraint at the end of the search, and we just pick the feasible one. Okay, so one issue with this search is that For the system with good logging, for example, the VCL, usually they generate a lot of console log messages during the production run. In-situ perform very well. However, from some other system, such as some open source software, they usually generate very few console log messages. I'm showing here one example of a failure in CoreUtils. It's only 2 console log messages for this failure. So you can imagine that between these 2 console log messages, there might be thousands of instructions. So it needs to multiple possible paths. And because inside doesn't know which one is pick among these multiple possible paths. So our idea is that we want to provide more actual information for inside so that it knows which is the right one it should pick. Here we use system call sequence as a guidance between 2 console log messages. So again, same example. If we know the system call sequence between these 2 console log messages is sit pro, sit read, we would only allow the path, so during the search, we only allow the path that generate the same sequence of system call. For example, the first one generate the wrong sequence, so we just drop it. Second one generate the correct one, so we pick it. Okay, so right now we only support Perl and C++ program. The reason we support Perl is because the VCL is written in Perl. In order to perform guided by execution exploration, we modify Perl interpreter, basically to add handling for the branch opcode, and we manipulate the stack to change the branch condition. We do the same thing for C and C++ program by using a pin tool to intercept branch statements, and we change branch condition by manipulating the EF flag register. So for monitoring the system call, we use system tab, which is the lightweight monitoring tool. So here is a setup failure we tested with our inside system. The first 4 are from the VCL system, which is basically production failures we found in the log. The rest are from open source software. We found it in the online bug repository of each system I'm showing here. So one thing we can see is that here we can see the VCL generated much more console log messages compared to our open source software, ranging from hundreds of console log messages for each failure. So first result I'm showing here is the cone by difference. So basically it denotes the deviation between the cone sequence of the path discovered by inside and the cone sequence of the original failure path. So we tested inside with 3 different environment settings just to understand how the environment would impact on the inside. The first is the complete environment information. In here, inside have all the original information at the failure run. The partial environment information in VCL system, we just simulate this by dropping all the information in the database that related to the fail request. For the low environment information, we basically drop all the information in the VCL database. So we can see here is that for the complete and partial environment settings, inside can always find out exact call path. For the no environment setting, basically just simulate the offline failure reproduction. We see that inside can only find out for one case. The rest it couldn't find out. So that's clearly show the benefit of doing in-situ failure path inference. Next, I'm showing the result for open source software. So here we also tested inside with 3 different settings on input and amount of information we provide to inside. So original inputs mean we assume that inside know what is the original input that trigger the failure. The same input type basically is very similar. It's kind of similar input, but it doesn't trigger the failure. One example I can tell you is that for Apache failure case, the same input type, we just use a normal web request that I set a web page with correct authentication setting. So we test inside with console log only, with console log and system call. So we observe that with original input, inside can always find out the exact call path. With same type of input, inside can find out the very similar call path with for the mode cases. However, for some cases, like the first 2 cases, with console log only, inside there's some deviation in the call path. With the help of system call, we can find much better the call path, much similar call path. As we can see some difference here, we were wondering whether the code path we found is still helpful for debugging the problem. So we manually examined the code path, and we found that all the code paths cover the root cause branch and function and branches. We also have the result, detailed result for comparison between the other branch level. You can check out our paper. So here's the failure plus inference time. So it includes the scenario creation time and the binary exploration time. So In-situ can achieve very fast cert within minutes. So lastly, I'm showing here is the overhead of In-situ. That's In-situ my impact on the production system. Well, for the scenario system, it's about 0.3%. With system culture is using system type is about 1.5% for Apache. So with the log we use in Apache 50 requests per second. There are some results for logging overhead here, so it's very small compared to the modern storage nowadays. So to conclude my talk, I present In-situ, an in-situ system to enable failure path inference inside the production environment. We use we use scenario component to decouple analysis from the production run. That's to minimize the impact on the production system. And lastly, we use guided by execution exploration to leverage the environment information to find out the high fidelity path within a minute. So thank you. I would like to take some questions.